NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hey, good evening, ladies and gentlemen. How's everyone tonight? Yay, good. Well, thanks so much, as always, for coming out to join us, especially on this very lovely December evening. So, shall we? The original Gravity Recovery and Climate Experiment, or GRACE mission, which began orbiting Earth in March 2002, has provided Earth scientists with an unprecedented view of changes in our global water cycle and allowed precise determination of sea level rise, ice mass loss in Greenland and Antarctica, and large-scale water storage changes over land. These discoveries provide a unique view of Earth's climate and have far-reaching benefits to society. The twin satellites of the GRACE follow-on mission, scheduled for launch in early 2018, will continue this extremely successful work while also testing a new laser technology designed to improve the already remarkable precision of its microwave measurement system. Tonight's talk will present the fascinating technology behind gravity measurements from space, review some of the most exciting and surprising findings from GRACE, and provide a peek into what might lie ahead with GRACE follow-on. Our guest tonight is a research scientist at NASA's Jet Propulsion Laboratory. He earned a degree in geophysics from the University of Kiel, Germany, a doctorate in physical oceanography from the Max Planck Institute for Meteorology in Hamburg, Germany, and was a NASA postdoctoral fellow at JPL from 2008 to 2010. He studies Earth's constantly changing hydrosphere by using data from various satellites to understand global and regional sea level variations and provide relevant data for water availability in a changing climate. He has published numerous high-impact scientific papers on these topics and is currently the Deputy Project Scientist for the GRACE Follow-On Project. Ladies and gentlemen, please help me welcome tonight's guest, Dr. Felix Landerer.
Thank you. Well, thank you, Mark, for the introduction. On behalf of the GRACE Follow-On Project Science team, I welcome everyone here to this talk. It's a great pleasure to give this last and final lecture, Von Karman Lecture, in 2017. I understand we have some unfair competition tonight. The Star Wars movie, I think, is being released, so whoever planned that. But I'll try to make your time here worthwhile, and what I want to do is tell you a little bit about our GRACE Follow-On mission that's coming up, how it works, and give you a little bit of a sneak peek what we're trying to learn and how we want to continue what we've learned from the very successful GRACE mission that flew until just very recently. So GRACE Follow-On, just as GRACE, is a collaboration between NASA and Germany. GRACE Follow-On is a collaboration with the German Research Center for Earth Science, GFZ, with support from the German Space Agency, DLR. As Mark mentioned in his introduction, I'm a physical oceanographer. So, when I went to grad school, I was thinking about what I want to do, what I want to study. I liked the outdoors. I had an affinity to water, so I did the natural thing, combined the two. That's not actually me, but I started studying physical oceanography, and of course, you go where the signal is. You travel the world's ocean, and that was an adventure in every respect. It was fun, but as it turns out, being on the ocean for weeks, sometimes months on end, it's literally hard to stomach at some point, because this is a nice still image, but the ocean is not that still. And believe me, after a few weeks of this, you are sick of this. So I presented my results. I studied sea level and ocean current changes at a conference, and I got to talk with a research scientist here at JPL, and she invited me to come and extend my studies at JPL and kind of slightly change the vantage point. And rather than having to be on the ocean, I could go up to space, still continue to study the oceans, but use remote sensing. And I was fortunate enough to come here at JPL during a time when the GRACE mission was sort of at its peak and collecting very unique, novel data, and had the opportunity to really study unseen things with the GRACE mission. So, as Mark said, the GRACE acronym here stands for Gravity, Recovery, and Climate Experiment. And this is the follow-on mission. And what it does, it provides us a view into the Earth's water cycle. And when I say water cycle, each one of you might have a different mental image of what that is. You might think about water running down streams and rivers. You might think about rain puddles, water draining into the soil moisture. It's probably not the image you have right now here in Southern California. You might think about snow. This is water. A different form of water, has, of course, different characteristics. This is part of the water cycle. It's the absence of water. And, of course, we all know that humans critically depend on this vital resource, and if it's scarce, it triggers potentially disastrous effects. Here, this is from the Dust Bowl, this image. Humans have started to interfere with the water cycle in some sense on a pretty large scale. We now use water for irrigation. We drill deep wells, here in particular in the Central Valley in California. You are probably all very well familiar with this. So this is part of the water cycle. You might think of icebergs, ice sheets, glaciers as part of the water cycle, and justly so. They are part of it. They constantly draining into the ocean. They're being replenished at higher altitude when it snows. So this is a very dynamic system. Part of the water cycle is also the oceans. And as I sort of showed in my introduction, they're moving. It's not just waves. Storms cause storm floods. Sea level is rising. So the main point about the water cycle is that all these things are connected, of course. Right? This is just a picture here of the main ingredients of the water cycle on our planet. Water evaporates over the oceans. The vast majority actually also precipitates again over the oceans. But then it is transported over land where it rains, either snow or rain. It makes its way into the groundwater, percolates deep down. So all this is water, but it has a very... Each component here has different characteristics. So if you want to measure this from space with remote sensing, it's difficult to exploit, for example, spectral characteristics of these water components because there are such different forms. Some you can't even see. They're underground. But what they all have in common, of course, they have mass. And everything that has mass has a gravity field. So we're exploiting the concept of gravity to track the movement, the motion of all these water components through the entire Earth system. And I just want to, in the next couple of slides, give you a little bit of an introduction to how we do that and convey the concept of how we measure gravity changes and, by extension, mass changes with GRACE and GRACE follow-on. So this is Sir Isaac Newton here in the late 1700 or so. The story goes he was hit by an apple as he sat in the yard. That's probably not exactly how he discovered gravity, but let's just go with this image for now. So he realized everything that has mass, and it was the apple. The motion, the movement of the apple, if you could measure the rate at which this apple drops, you can learn something about the mass of the underlying body, the Earth in particular. If you know the mass of the apple, but the rate at which this drops, the force by which this is accelerated downwards is just a function of the apple's mass and the Earth's mass here, m1, m2, and the distance, inverse squared, the r. And I promise this is the only formula, is the only math I'll show tonight. But so if we can use this apple or something like it to measure gravity, then that's kind of remote sensing of gravity. So, as I said a few minutes ago, ice water has mass. of course. So if we could replace the Apple with a satellite, that's our remote sensing tool. So now, of course, we don't want to drop the satellite all the time. That wouldn't be a very useful concept to measure gravity that way. But what people realized, and this concept actually goes back to the late 60s here, is that if we tack on a second satellite, equivalent to the first, as these satellites fly over this mass underneath, they're being affected by the distribution of mass a little bit differently because they're in a different location. So each satellite feels this mass slightly differently. And what happens then, as they orbit the Earth in this case, they do a range change, or they undergo a range change. Their orbit is perturbed. And that is really the core concept that we're using, that we're exploiting for this gravity mission. And just to illustrate that a little bit further, if you imagine these satellites, of course they're not flying that low, coming in from the right here, as they fly and orbit over the mountain, and the mountain is a mass anomaly locally. So this is heavier here, there's more rock, more snow, for example, relative to here. As they progress, you see that the distance changes, right? This satellite gets pulled towards the mountain a little bit more than the trailing satellite. So the range, the distance changes. As they progress, the distance becomes a little bit less again. And when they are here, this satellite is kind of held back by this mass now. This is further away, and it looks like this. So if you plot the range change between these satellites, it would look like something like this. They're being accelerated towards each other, and they slow down and accelerate it again in the other direction, and then they kind of go back to normal. So this is really the fundamental and quite, in a way, very beautifully simple concept that we're using to sense mass on the ground and mass changes on the ground. On orbit, this looks a little bit different. So we'll start this animation here. The satellites fly in a near polar orbit at about 500 kilometers altitude. The separation between the satellites, they're actually not that close. They're about 220 kilometers apart. So that's sort of from here, Pasadena, to San Diego. And as they orbit the Earth, they constantly do undergo these range variations, or this dance. Sometimes we call this dance. So the concept of the measurement is not so much that they go up or down. It's really just the orbit velocity that is perturbed, and differently so for each one. And what's shown here is they're not tethered. The way we measure the range variation is with an interferometric measurement. We're using a microwave interferometer. So these are electromagnetic waves. And the range variations are actually very small. What you saw here is greatly exaggerated. The range variations are actually a few micrometers. And I'll show you a couple of examples down the road. GRACE Follow-On will not just have a microwave interferometer, it will also use a laser ranging measurement. So laser ranging is much the same as when you buy from Home Depot, for example, these things where you can measure the distance to a wall. So works in a similar concept, but it's much more accurate by a factor of 10 to 20 than the microwave interferometer. So that's a novel technology demonstration on GRACE Follow-On that we're pretty excited about. And here you can see sort of the artist's view of where we are hopefully going to be in a few months from now. And in the middle here, this white line depicts the microwave interferometer. That's really our workhorse. And then the laser, sort of a round-trip measurement, is a new technology on GRACE Follow-On. So how does this actually look like when we measure the gravity in that way, when the satellites orbit at that altitude in the polar orbit? So we get about 15 orbits per day. It's about 90 minutes per orbit. Satellites travel at 7.5 kilometers per second, so that's about 4.4 miles or so pretty fast. And you see, for one day, we don't really get a global coverage. We get some nice ground tracks, but we want to really measure the mass change or mass field globally. So after 15 days, of course, we get a much better coverage, but it's not quite enough yet to make a gravity field. After 30 days, we really get dense enough coverage to get a good gravity map of the Earth. So if we take those 30 days and some prior knowledge of what the Earth's gravity field looks like, and we plot that, and what I'm showing here is the Earth's gravity field, and it has negative numbers. Of course, the gravity field is not negative; it's always positive. But I've subtracted the constant part of it, or the ellipsoidal part of it. So the part that doesn't have any lumps and bumps. If you just have a very clean Earth that doesn't have any mountain ranges or any mass anomalies in the crust, for example. So this is for August here, 2006. This data actually comes from GRACE. And I said we want to track the mass changes. So we just repeat this again a month later, and then we can track the difference. It looks like that. And you can clearly see the difference. Or can you? No, you cannot. These images are actually different. These are different data. But you can stare at this all day. You won't see a difference. What I need to do is I actually subtract these two images from each other, and then it looks like this. And now you can suddenly see a very different signal. I've really blown up the color scale here by several orders of magnitude, right? So all the differences here are in this very small range. And whereas in these two images, you see very different features. What you see here is, for example, the high Andes Mountains. So that's that mountain range that you saw in the beginning where I showed the concept. You see the trench tectonic feature. This is a subduction zone. This is where it's a negative anomaly. But of course, these things don't change going from August to September. They're part of the static gravity field or the constant gravity field. But what does change are signals, for example, in the Amazon. So here, this red blob, it's negative. It's a reduction of the intensity in the gravity field. And what that is, as we go from August to September, we're entering the dry season of the Amazon. So water that was in the Amazon basin has run off into the ocean. There's less water, there's less mass, and our satellites can sense that. And this is why the GRACE and the GRACE follow-on mission are so important to track the Earth's water cycle, because we can now reveal these features, and we can make maps month after month and really track the motion throughout the globe. You also see features here over the oceans in smaller amplitudes. Those are related to ocean circulation. For example, there's a recirculation region here. So we can also track that. As I've already alluded to, GRACE follow-on comes on the heels of the very successful GRACE mission that flew over the last 15 years. Sadly, it finally ended just a few months ago in 2017, June. We got our last gravity field due to the age of the satellite and aging batteries. But GRACE really has a very exciting data record over 15 years, a really unprecedented view of how the Earth system works. And in particular, it revealed how much the ice-covered regions are changing on our globe, Greenland, Antarctica, the glaciers, and how aquifers are changing. So I'll show a few examples of what we learned from GRACE and kind of allude to what we hope to learn from GRACE follow-on. Here I've plotted the entire GRACE data record. Of course, you can't see a whole lot. That's not the point. What I want to point out is that we now have over 15 years of monthly snapshots on how the gravity field of the Earth changed. And bluish colors here denote areas and regions where mass increased, and that mass increase is almost always water, and reddish colors where it decreased. So you probably get dizzy looking at this. So I just want to highlight a few things that Earth scientists have learned over the years. One of the first things that we discovered, I already alluded to this in the previous slides, is the seasonal cycle in hydrology. Now, we didn't discover the seasonal cycle, but for the first time, we were able to actually accurately measure the mass change, weigh the mass changes related to water. Before that, hydrologists had field measurements, right? You have to go into the Amazon, and good luck with measuring how much water is in the entire Amazon basin and how it's changing. That's virtually impossible. And GRACE does not care about whether there's a canopy or whether the water is underground. We really, through gravity, get the total water storage. That's really the essential part and the unique angle that GRACE and GRACE Follow-On provide. So the hydrologists learned that, what is the signal amplitude as we go from the wet to the dry season and then from the dry again to the wet season. This was quite novel. Of course, this doesn't just work for the Amazon. This works anywhere in the globe because we get global maps. The other major discovery that was made with GRACE is that for the first time, as you go down here, so down is years, you can measure for the same time of the year changes over multiple years, trends, long-term variations. One of the main signals that we saw with GRACE was the ice melt from Greenland. So for the first time, we really could measure how much mass is coming off the ice. That's very hard to do otherwise. We can measure how the surface height is maybe changing, but then there's snow compaction going on. So it can snow, and when snow is fresh, it's very powdery, but as it ages, it compacts, but it might not actually lose mass, right? It just gets denser. So if you just measure the height of the surface, you don't get that knowledge. So with GRACE here, we saw massive ice mass loss. Another major application, I'm showing just one example here, is that we could put accurate numbers on groundwater extraction in very important regions globally. And this example here is from my colleagues Matt Rodell and Jay Falmayetti. They measured really for the first time the groundwater depletion in northwest India. And that paper caused quite a stir when it came out because contrary or different to maybe California, there isn't a whole lot of in situ or ground monitoring going on, right? So from space here, we can get this holistic view of what the water is doing. And while it's not shown here, more importantly, related back to maybe also what the mass change in of glaciers in the Himalaya mountains is maybe contributing to this. So those are really the amazing discoveries that we hope to continue with the GRACE Follow-On mission. And going back to this image here, you might have noticed that gaps are appearing since about 2011 in the GRACE data record. That's really when the age of the satellite started to come through. We had a degradation in the batteries, so periods of intervals of about 5 to 6 months, we had to turn the satellites off because as the orbit is progressing, these satellites undergo a period of sunshade. So when the batteries don't have enough capacity and the solar cells don't receive enough light, we can't operate the instruments. So that happened more and more often until finally in 2017 here in June, the instruments stopped working entirely. Unfortunately, we're going to have a little bit of a gap to GRACE Follow-On, but as I'll show you in a little bit, we're planning on launching GRACE Follow-On in spring 2018 and then continue that data record. And maybe just to highlight why the continuation of the data record is so important, this is an example here of GRACE measurements over California. So time is running here. And what you see is the total mass change in the San Joaquin Sacramento River Basin. This was our first dry period here, ended in 2010. We got a little bit of a reprieve, and then we entered this deep drought that you're probably all very familiar with, all the way into 2015, really dark. We had some good wet winters, but even after this record rainfall in 2017, we're barely back to where we were. If we tack on a little bit newer data, it comes up a little bit, but as you see with the current fire situation, we're still in a very dry regime. So another thing here to emphasize is you see a seasonal cycle here in the background. So this is going on all the time, right? We have the wet winters, snow accumulating in the Sierras, but then we also have these extended droughts. And as we enter these dry periods, what happens is that the farmers, of course, to irrigate their crops, they turn to groundwater. So There's a substantial contribution here as we slide into this drought of groundwater depletion in the Central Valley Aquifer. And one of the things our research scientists here and in other research centers are doing is using the GRACE data to really try to figure out whether the aquifer is getting replenished and what the timescale of that is. So this is very important work. And just want to highlight one more time. I've pulled out the snapshot at the peak, or the trough, I suppose, of the drought. So in 2017, this is when everything is deep red. We're in that hole. So I mentioned at the beginning the very small mass changes, the very small distance changes that GRACE needs to measure. So this relative motion change. If you imagine the GRACE satellites, they're going to come down here, overfly this region in a second. This is what they would see. So they're seeing this kind of whoop whoop, and the y-axis might be hard for you to see here, but this is in micrometers per second. So a micrometer is a millionth of a meter. Your hair is a few micrometers thick. So these satellites are 220 kilometers apart, right? And they measure the distance change to the fraction of the thickness of a human hair. That's even working after 10 years on this, it still always boggles my mind how that is possible. But it is. So, 50 gigatons of water, that's a lot of water. That's more than one entire Lake Mead that was sort of lost here on the ground is just a couple micrometers where the satellites are in orbit. But this is what our technology can measure. I alluded to the fact that we get these measurements globally. So here's a map. This is based on a publication by my colleague Jay Famlietti here, who's the lead of the Water Research Center at JPL. What they did is they pulled out the GRACE observations and they looked at the long-term changes over the world's most important aquifers. So those are the deep groundwater reservoirs that are often used for irrigation. I showed you the one here in northwest India. So everything here that's sort of yellow to orange to red, those are aquifers that are under stress. Mass is decreasing in those aquifers, which means more water is being pumped than is being replenished on these long time scales. And of course, these are not endless reservoirs. Water has to be drilled deeper. As you drill deeper, you might dredge up some unwanted contaminants. You also see other regions here that are in the blue. So these are gaining mass. But this is, of course, over just a time period of about 10 years in this case, or 11 years. So how this is evolving over time is something that we want to track, for example, with the GRACE follow-on mission, because there's quite a bit of variability. And this data has become a vital resource, not just for scientists, but also for agencies. For example, the U.S. Drought Monitor is assimilating the GRACE data into their drought monitoring system. And so are other agencies, in particular here in India, in the Middle East, and Pakistan. One of the perhaps most iconic data records from GRACE, or revelations from GRACE, is that of ice mass loss over Greenland and Antarctica. So I'm going to show you this movie here of what we've seen, what we've measured with GRACE over Greenland. What you will see in a minute here is the colors changing over the ice sheet, and it's a little hard to see. There's some flow lines here. And I think the image or the movie really speaks for itself, because over the 15 years of measurements that we have with GRACE, we just see a major ice mass loss over Greenland. As time progresses here, there's always a little bit of accumulation in the winters, but a much bigger drop in the summers, right? So this is slowly draining your bank account. More mass is coming out than is being replenished in the winters. And as we enter these deep shades of red here, so all these are areas of mass loss, you see that there's a certain pattern to this. It's not uniform. It's not the entire ice sheet. It's just losing mass. And I don't know if you notice this. I'll play it again, if I can. There are these flow lines here converging, and they're converging in those areas that are going to be the deepest shade of red. So what these regions are, just focus here, for example, or here, These are regions of outlet glaciers. This is where the ice stream is converging, and actually there are these fjords here. At the end of the ice stream, the ice is calving into the ocean. So the ice stream is in direct contact with the ocean water. And of course, this pattern here provoked the theory, the idea, well, maybe the oceans have something to do with this. So what our research scientists here are doing now, in particular Josh Willis, who might be a familiar name to some of you, they are probing the oceans in front of these outlet glaciers. Josh is running a mission called OMG, Oceans Melting Greenland. So we're using remote sensing to assess the temperature changes in the ocean. So they're going into these fjords with airplanes, and we're dropping these sondes into the ocean, and they're sinking, and while they're sinking, they measure the temperature and the salinity, then they pop back up, relay their data to satellites, and what we can then do is combine this data from GRACE and OMG and feed it into ocean models and really try to understand what's going on. Because GRACE gives us the mass change. You can say, well, great, that's the mass change. But why is this happening? What is happening? And most importantly, perhaps, where is this going? Is it going to go like this? Is it going to come back up? And that's obviously very important for future planning. The mass loss here, we always use this convenient unit of gigatons of mass loss. So Greenland has lost almost 4,000 of gigatons over 15 years. At a rate of about 280 per year. So everyone always asks, well, what's a gigaton of water? So, well, a gigaton of water is a pretty large cube of water. If you drop that on New York City, this is 1 gigaton, just one. So Greenland has lost 280 of these year after year over the last 15 years at a pretty steady pace. If this doesn't speak to you, this image, this is about 400,000 Olympic swimming pools. So at the rate at which Greenland is melting is about 8 of these swimming pools every second. That's a mind-boggling number. Why do we care? Well, this water just doesn't, or this ice just doesn't disappear from Greenland. Obviously, it goes somewhere. It goes into the oceans. I don't know if you saw the difference here. Sea level is going up. In this animation here, sea level has gone up quite dramatically. This is what we call an extreme sea level scenario. Sea level has risen by more than 8 feet in this scenario. This is a simulation. So one of the main questions that scientists have, and actually all these people that live here, is this realistic? Is this plausible? How likely is this? Well, and when will this happen? Do we have to worry about this? So what I'm trying to underscore here is that the data that we collected with GRACE and that we want to continue with GRACE Follow On is really trying to address these key questions, at least for the ice sheets. And these 8 feet scenarios, they're very extreme. They're very at the high end, but increasingly we think they're plausible. Maybe not likely, but plausible. So they're not just pure fiction. But the question really is, are we talking about 50 years? Probably not. 100 years? But maybe 200 years or so. One of the great things with GRACE, and GRACE Follow On by extension, of course, is that we can also track the global ocean mass. We get this global picture of mass change. We track it as it goes from the ice sheets into the oceans. And we have other missions, for example, here the JASON-3 mission that is flying right now that measures the height of the ocean. So where is the surface of the ocean? The curves that you see here are the so-called global mean sea level curves. So if you live by the coast, this is really the curve that interests you in the global mean sense. And these altimeters, we call them, they send a pulse down, a radar pulse, and bounce it back to the ocean. And as sea level changes, of course, the travel time here changes, and we can measure the height change. Sea level has been going up by about 3 millimeters per year. It doesn't sound like much, but this is happening globally everywhere. It's actually not uniform. There are some regions that go up much faster. Some regions go up less so. But if we combine this with the GRACE data record, we can tell how much of this increase is actually due to mass. And it turns out about 2/3 of the current sea level increase is due to ocean mass change. So that's mainly contributed by the melting glaciers or ice sheets that I just showed you. This other third is ocean warming. This is the thermal heat uptake and expansion of the ocean water. And if we actually combine these two measurements, we can also tell how much the oceans are warming, really without ever actually having to measure the temperature change. So we can use sea level as a proxy for ocean warming. And that's one of the applications that we're pursuing with GRACE and GRACE Follow-On. Also, just want to highlight again here that the measurement concept of GRACE and GRACE Follow-On is really quite different from other remote sensing tools that we have, because we really do our measurement on orbit, at altitude, right? We don't bounce anything off the surface. It's really just the distance variations of the satellites. And as such, the satellites, you can think of the satellites themselves as the experiment, as the measurement. That's a very unique concept. And by the way, this works not just on Earth, works on other planetary bodies too. So a pair like this has been flown around the moon. This was the GRAIL mission a few years ago, also here out of JPL, and yielded very successful information on the gravity field of the moon. But that's not the topic tonight. You might have noticed here that this curve has a couple of bumps. One of the interesting science stories that GRACE discovered was this big drop here in 2010. So you can imagine if you go back to 2010, we're right here, and all of a sudden sea level starts going down. And of course, everyone's like, whoa, what is happening? And where's this going? Is this the big, is this the end of global warming? We're safe. This will not continue to rise. That was sort of one thread that emerged. So if you just see the drop with the altimeters, you don't really have any insight on what is going on. But at the same time, ocean mass also dropped. And if ocean mass drops, it must mean the water is somewhere else, because it can't just disappear, obviously. So in this time, in 2010, we had a big La Nina event. So La Nina, El Nino, you might be familiar with those terms. Those are large-scale global climate phenomena that impact the pattern of precipitation and rainfall. So this event here shifted the rainfall pattern such that we had a lot more water over regions where we typically don't have a lot of water. This upper map here shows the situation in early 2010, so 2009, 2010. And you see some high water storage changes here in South America, a little bit of a low here. But by and large, this averages out. By 2010, going into 2011, this map looks a lot more blue. So there's a lot more water on land, hence the sea level dip. And in particular, Australia received a lot of water. These were record-breaking rainfalls in Australia, rarely seen there. And what happened is Australia is quite unique in its hydrology. It's a very dry continent, in the interior at least, and it's a little bit like a salad bowl. It's called what the hydrologists call an endorheic basin. It doesn't really drain well because of very flat, shallow topography. So the only way for the water to get off is to evaporate. That, of course, takes longer than to run off. So for a year or so, a lot of areas here in Australia were inundated and flooded, and all this water was stored on the continent and lacking in the ocean. Eventually, of course, it made its way back into the ocean. But this was a very nice assessment and analysis of the water cycle and how the various components are coupled and interacting. So I've talked quite a bit about the science data record that we got from GRACE over the last 15 years and the insights that has yielded and how we want to continue that going into GRACE Follow-On. I now want to turn to the actual GRACE Follow-On mission and tell you a little bit about the instruments and look under the hood of these quite beautiful satellites and tell you a little bit about the technology and also how it has evolved from GRACE to GRACE Follow-On. So to look under the hood, we have a very good graphics department here. these nice animations. We can peel away the cover and look inside. And you will see here, one of the core instruments is the so-called microwave interferometer. This is how we measure the distance. The laser ranging interferometer, this is new. I'll talk about that in a second. The accelerometer, this is a key instrument. Star cameras, those give us orientation in space. A GPS antenna, also for precision orbit determination. And then we have another occultation antenna here that measures temperature profiles in the atmosphere. Weather forecasters use this. This is not really related to gravity, but the orbit of the satellites, the GRACE satellites, is quite low. So we learn a lot about the lower parts of the atmosphere, or the upper, relative to other satellites, the lower part of the atmosphere that way. So in this CAD model here, only really the key instruments are highlighted. If you look at the actual satellite, it looks like this. It's packed. This is really a very densely packed spacecraft. So just to orient you here, this is the spacecraft rotated on its side. The solar panels have been removed. You see the tanks here for on-orbit corrections, for a little bit of propulsion. You can see here this microwave interferometer. So in this animation, it was pointing the other way. You see here this laser ranging interferometer, these tubes here. That's where the laser light comes in. And there is what we call a triple mirror assembly, because what we use as a measurement principle is interferometry. So we need to combine the incoming and outcoming beam, and any little phase shift tells us about the range variation that these satellites undergo. I mentioned the accelerometer that actually sits here literally in the center of mass of the satellite under this thing. It's a very important instrument. It's very small, but it's a proof mass, and we have to really make sure that it's in the center of the satellite. And this proof mass is the key reference point to which we reference all the measurements. And you can see here the head of the star cameras. There's one, there's the other, there's the other. So these star cameras look out the whole time, and they have a star camera catalog on board. So as the satellite moves a little bit, we need to back out that movement, and the star cameras allow us to do that. And you can see here all these ancillary computers, really a very packed spacecraft. I mentioned the laser ranging interferometer as a novel instrument. So GRACE didn't have that. GRACE Follow-On is really the first mission that will do spacecraft to spacecraft laser ranging in orbit. And this is, in its core, also the same technology that, for example, is going to be employed in future missions to detect gravitational waves for the LISA mission, for example. So the engineers that are working on this are also working on LISA project, and they're very keen to see how this performs. If you compare this to the original GRACE instrument, you can appreciate that this is much less densely packed. It's the same bus, so it's the same dimensions. We didn't want to change that because continuity of the data record was key for us. So we didn't want to change the sort of aerodynamic properties of the spacecraft on the outside and utilize the spacecraft bus, with which we had a pretty good experience. But if I go back here to GRACE, you can see that with all the upgrades that we've done, it's becoming pretty densely packed. Just a few more pictures here of the engineers integrating all the instruments. These spacecraft have been assembled by Airbus in Germany. The instruments, here's this microwave interferometer, are contributed by various institutes. This microwave instrument is from JPL. You can see here some integration. I think this is I'm actually not sure whether, I think this is part of the laser instrument. This is this triple mirror assembly, so and the star cameras all in one compact unit. And one of the great things of working at JPL is, I don't just get to show you these pretty pictures. As a scientist, I'm not allowed to touch anything, of course, but I really get to be close during the integration of the instruments and be part of that. And that's a nice memory to have when you're working on this, but it's also vital for me as a scientist to have an idea of where the instruments are located relative to each other on the satellite, because all the data that will come down We'll have environmental data about temperature changes in the satellite, about calibrations that go on. So for me as a scientist, it's very important to have a good intuitive understanding of how the instrument actually looks. And right, when I talk to engineers and they speak their jargon, helps me to map that into what I saw there. These satellites, as I mentioned, have been built and assembled in Germany by Airbus and over the last few years. And in 2017 in particular, have undergone rigorous testing. Here's an image of so-called acoustic tests. So the satellites are already strapped to this thing here in their launch configuration. And this test is to simulate the acoustic loads during launch. Right? It's a very intense phase, very loud. We need to make sure that what the instruments experience inside of the satellite is within specs, so nothing breaks. We have very sensitive instruments. That's critical for us to verify. So all went really well in these tests. Here is a so-called fit check. We have a satellite dispenser, so this gets stacked on top of the rocket, and these are just mock-ups. These are not the real satellites, but we're just checking that they fit on the satellite dispenser. There are little pyro shocks here that will fire once we're in orbit and release the satellites. And that also gets tested. That's pretty dicey. These are the real satellites, or one at least, on this multi-satellite dispenser. And the pyros actually get fired in the lab to really verify that they release properly. And all went really well in these tests. I'm quite happy. Because the thermal properties of the satellites are so important for stability, because we need to make these fine measurements. The satellites also undergo very rigorous thermal balance and vacuum tests. This is in a test facility in Munich. So they get put into this big chamber here, the door gets closed, and a near space environment is simulated. So it gets pumped down near vacuum, gets then blasted with a sun-like source to assess how the temperature changes, what kind of temperature changes occur in the satellite, and to verify that everything is within the spec. So all went really well. I think we have two very beautiful spacecraft. They're very elegant. I'm a little bit biased maybe, but it's really excited for launch. And just, what's today? Thursday. 2 days ago, this cargo plane landed in Vandenberg Air Force Base here in California with the two satellites on board, because we're launching out of Vandenberg in spring. So they were transported to Vandenberg, made it here safely. This somewhat beautiful sunset, I think, is really just the fire smoke in Santa Barbara out there, but the satellites made it safely. And our engineers and the Airbus engineers are in Vandenberg right now unpacking the containers and getting ready for the so-called integration of the satellites, getting ready for launch. That is in spring 2018. You can follow the launch, as always, on nasa.gov, NASA Live. And I mentioned that we're launching on the Falcon 9, but this is also a first for NASA, I think, that this is a so-called rideshare with a commercial partner, with Iridium. So we're going to share a rocket, and there will be a stack of 5 Iridium satellites on the bottom. Our 2 satellites are on top of that. It's quite challenging to do that. Moreover, we need to go to different places on orbit. We get dropped off first at about 490 to 500 kilometers. We get popped off, and then the second stage with the Iridium satellite still on it does a little dogleg and goes to a somewhat higher orbit. After successful launch, there's a 3-month so-called in-orbit checkout phase where our instrument and science teams will successively power up the instruments because of the need for the satellites to actually fly in tandem. Right? We need to position them correctly. We need to verify the alignments. We need to acquire the microwave and the laser links. So all this is well planned out. There's a whole protocol in place. And hopefully in the June-July time frame next year, we'll start producing our new gravity maps and be able to continue that very successful GRACE data record. So with that, thanks for coming out. More information here is on this website, gracefo.jpl.nasa.gov. I think we're going to frequently update that as time goes on and as we successfully integrate the two satellites. Thanks for coming. So I'm happy to answer any questions that you have. So I think if you have questions, please use the microphone so people watching online and in the room can hear you.
Hello? Testing? Hello?
I think it's on now, yes.
Okay. Weren't there other satellites that I asked you earlier? I thought it was going ground to satellite, but I was sort of surprised that it's a difference in their differences in their space between them, each satellite. Yes. Weren't there other missions before that actually could tell up to a meter difference in different oceans?
So we have multiple instruments, right? So the ones that do a remote sensing down by reflection of waves in the electromagnetic spectrum, radar, or even thermal imagers. So our satellite altimeters, they can measure sea surface height changes of a few millimeters. So they're that sensitive.
Okay.
The ranging measurement that we do with GRACE, because we sense the gravity at altitude, so the gravity decreases as you go away from the source by 1/r². So we need to be very, very sensitive to that, or that change becomes very small at altitude. We could go lower with our satellites, but then we're going to encounter atmospheric drag, and that will, for one thing, reduce the mission lifetime. They will come down much faster. It will add noise to the system, so we're kind of trying to hit the sweet spot. Go as low as possible, but still have an altitude where we get a good signal and as little noise as possible. Does that answer your question?
Yes. I sort of have a follow-up, sort of related. It seems to me when you started talking that one of the beauties of measuring water, it's one of the most dynamic changes of mass upon the Earth's surface, right?
Yeah.
Okay, that's, not intuitively makes sense. That's why we would look at the water so we get all these other measurements too.
So I've and I want to allow a few more questions, but let me just add that. So I've talked about water as being the main source for the gravity changes that we observe. Of course, other things other than water change over time that cause mass shift and hence gravity changes. One example would be large earthquakes when you have tectonic plates that suddenly do this. So we also have detected those with GRACE, and our solid earth research scientists are using that data to learn about earthquake mechanisms. So of course it allows us to look at sort of maybe there are precursors, but more interestingly, while plates shift during an earthquake, there's also a long adjustment time afterwards over multiple years. So you can learn about solid earth properties, about the elasticity of the solid earth also from GRACE.
Thank you. Can you talk a little bit about how you discarded GRACE, how you got it out of its orbit, and also how much it costs to catch a ride on the SpaceX Falcon 9?
You can probably look that up. So your first question. So I said the GRACE mission has ended. The satellites are actually still up there. They have been decommissioned, but they're what we call pacified. So they're no longer actively steered. And everything that goes up must come down if it's not fired up with escape velocity. So one of the GRACE satellites will probably re-enter and burn up. So it will break up and disintegrate and hopefully completely burn up in the next 2 weeks or so. It's that low. And the other is probably going to follow in January. Right now, because they're uncontrolled, they're tumbling, so it's kind of hard to predict that. But we let, gravity, ironically, will get rid of them. They will just fall out and due to friction, heat up, burn up. And your other question was about the cost?
Yeah.
So I don't know the exact numbers. I think you have to look that up. I don't want to blurt out a number here that's not quite right, but if you want to follow up later, I think we can look that up. That information is available.
Thank you.
Does cloud distribution affect your measurements at all?
That's an excellent question. Clouds, of course, are water vapor, so they have a mass. Compared to what's going on the ground in hydrology, that's not a whole lot of mass. We're not sensitive to, because we're not using radiation, clouds or gravity penetrates clouds, right? So they're not a barrier in that sense. We are removing from our measurements the effects of the atmosphere with atmospheric models or weather models. Those models are good enough to peel back that layer that's in there. But overall, there isn't a whole lot of mass, at least in terms of water, in the atmosphere.
Do you think about using this technology on a few of Saturn's moons, for example, Enceladus? I guess the problem is I guess the environment is much more severe, but still, it's very interesting if we could use that on some of the water moons.
Yeah, of course. I mean, one of the things that's necessary is to very accurately track the satellites and do a precision orbit determination. So, but any satellite, any body that orbits another is affected by its gravity, and the orbit is perturbed. So you could do this with just one satellite, and in fact this has been done. The orbit perturbations have been used to assess gravity or the gravity field of Mars, but there the gravity field doesn't change that much because we don't really have water. It's not so dynamic, right? So you can observe it for a longer time and you get that static field. That's what I showed you between these two maps. You get the static field. So this is being done. I'm not aware right now that we're really looking at the sort of two spacecraft ranging idea on other planets. But if there is, for example, more indication that there is an ocean and that it's active, right? I think you can make the case that this technology might enable to study that ocean.
Thank you.
The noise floor of your instrument must be very impressive. I'm just wondering if you can express it in terms of
water height,
discriminating the
vertical. That's a good question. I didn't really talk about that. So you might have seen in the maps that they're a little bit blurry. So we get a resolution on the ground of about 200 miles, 300 kilometers. That's sort of our footprint. We don't really have a footprint, or we don't think of it as footprint, but within that radius, you can resolve a water mass change on the order of about ½ an inch. So about this much. So you just think of a water layer that much, so we can sense that. The laser ranging interferometer, which you see here, I mentioned that it's about 10 to 20 times more precise in the ranging measurement. So that will help us to get a better signal-to-noise ratio. And it's really also the technology demonstration for future gravity missions, where we can then, for example, lower the orbit, fly drag-free. That's another technology. So if we combine those two, the laser and drag-free technology, we can really resolve even finer in a spatial scale, but also get even down to lower amplitudes that we can sense.
Very impressive.
Thank you. You got to thank all the engineers. I'm really just on the receiving end of this mission as a scientist.
This is another engineering question.
Oh, okay.
In orbit, there are always some disturbances, like the moon and the sun and the radiation and all the things. And it depends where you are in orbit, on the other side or this side. And then also what happened when you measure the atmospheric, there's a question about the atmospheric. effect.
Yes.
But what about snowfall, for example? And what about hurricanes? Because this affects the ocean level. If you
Yes,
have a
it
hurricane.
does. So,
I mean, all this disturbance. I mean, and how do you keep the orbit itself? I mean, of course, I mean, when you start the orbit injection,
yeah.
over the years, the orbit is going to be changing, right?
Right, so the orbit can drift a little bit, but we have these two gaseous nitrogen tanks here. So we have some thrusters that allow us to correct for that. We also have magnet torquers.
Yeah.
So your first question, and let me slightly paraphrase that maybe. When our satellites are in orbit, so they're affected by gravity, but they're also affected by drag, solar radiation pressure, things like that. And that's where this accelerometer comes in. Well, we have this little proof mass, and that proof mass is effectively suspended in a cage. And now the outside of the satellite, actually I didn't use my prop here. No, I can use this. So the outside of the satellite, you know, does this little jitter maybe due to solar radiation pressure or drag from the front. But that causes a range change that's sensed. But that range change is not due to gravity. So we have to remove this, and that's where the accelerometer comes in. Because the accelerometer is kind of free-floating, and there are these electrostatic plates in that proof mass cage that keep that proof mass in the middle, and we measure the force that needs to be applied through the electromagnetic plates, and can back out that noise on the satellites. So we correct for that.
Yeah, especially with the thrusters, you get...
Yeah, exactly. All those measurements are acceleration on the satellites, but they're what we call non-gravitational accelerations. So those are corrected for. And that's why that instrument, even though it didn't really occupy a whole lot of space in that animation, is really key for this measurement. Yeah.
What about the snowfall, as I said, and the effect?
Well, snow is one of our key measurements. You know, in the Sierras, for example. So snow mass accumulates. Of course, that's a lot of mass. Hurricanes, we sense if there's a mass change, a sea level drop, a low pressure system. All that has an effect on the gravity field. So we can assess that. And some of our colleagues are now using the a long track variations in that range change as, you know, if we happen to fly over a hurricane to back that signal out, and we can fold that back into models and learn about hurricanes from a different angle, for example. Yeah.
Thank you.
So I'll put that down here if you want to come up afterwards and take a look. Are there any more questions? A couple questions online? 3, okay. Okay, so we have from X Animus, are lateral shifts ignored? If they can be pulled apart horizontally, can they be pulled laterally? Okay, well, that's a good question. So the satellites are flying kind of in tandem like this. So I think the question, if I understand it correctly, is that I explained this variation, but they also do this variation. So that's right. There is a little bit of that variation, and we can't really measure that well because our baseline is this way, right? So in some sense, we do have to ignore that, but there isn't a big pull on the satellites this way or that way. It's really a long track change. But it means we're not that sensitive to gravity changes that occur to the left or to the right on the track. And that's really why we need that dense grid that I showed. And we can't just do it after one day, because if we measure a range change, we don't really know, does it come from over here, directly underground, or over there? But if we have a dense enough net, and all that, by the way, gets fed into huge supercomputers, we can compute the mass change accurately where they're located. So next question is from Chris. How far above Earth do you need to be to avoid atmospheric drag? Well, so we start in an orbit of about 500 kilometers. That's also where GRACE started. And over its mission lifetime, GRACE, it decayed down to 400 kilometers. And I think anything As we get to below 400, 350, we really start to encounter atmospheric drag. We also get a better signal, so there's always this balance because we're getting closer to the source of the mass. But if we want to go much below that, atmospheric drag becomes an issue. And most importantly, the satellites will slow, or they would decay faster, so we won't be able to measure for a long time. There was another mission a few years ago called GOES, or GOCE, by the European Space Agency that used somewhat different technology, so-called gradiometers, and they had a drag-free system. But when you go to a lower altitude, you need extra propulsion on the satellite to enable a drag-free environment, or to compensate that. Another question from William: how many gigatons of water does it take to raise sea level by a foot? All right. Now you're asking me to do math in my head. So 1 millimeter of sea level rise is about 340 gigatons. So 340 of these ice cubes. I showed you that Greenland is losing about 280 gigatons every year. So that's just under a millimeter. So a foot. Even after 10 years, I can not escape my metric system. It's about 30 centimeters, something like that, so 300 millimeters. So 300 times, let's say 300, roughly, gigatons, right? So 9 times 10 to the 4 gigatons. So quite a lot of gigatons, but the ice sheets hold a lot of sea level potential. Greenland alone has the potential to raise sea level by about 6 meters, so that's 18 feet, if all the ice melted, right? We're talking about a long time scale now. Antarctica holds somewhat over 60 meters sea level equivalent, right? This is all that ice that's stored right there. So, yeah, I think I answered the question. If you don't have any more questions, thanks for coming. Happy holidays. I can stick around for a little bit if you have more questions, if you want to take a look at the model. We also have some souvenirs for if you need some Christmas presents on your way out to the right. And then, come back next year. Thank you.